From the campus of Stanford University.
People are worried about data. They're worried about their privacy and their security. They should be. We need secure systems.
This is the future of everything.
But we can't have a system that closes that data off. It is too rich of a source of inspiration, innovation, and discovery for new things in medicine.
With your host, Russ Altman.
Today on The Future of Everything, the future of earthquakes. Experiencing an earthquake, even a small one, is unforgettable. I've lived in California now for many years. California is pretty seismically active, and part of living here is experiencing earthquakes. They are very weird experiences that violate many of your most fundamental senses: seeing, hearing, feeling. I remember the first one I ever experienced was in medical school. I was in a theater-type lecture hall with sloped seats, so I had my feet... I'm kind of embarrassed about this, but I had my feet up on the seat in front of me, and there came an earthquake, and all of a sudden my feet were swaying left and right, left and right. It was my first earthquake. It was a transcendental experience. Then, a couple of years later, we're having a graduation party for my sister. There's a jolt, and one of our bookcases completely collapses into a pile of broken wood and books. All the other bookcases were perfectly fine. And this bookcase was the only one oriented in a certain direction where the movement caused it to shatter, whereas all the other bookcases were absolutely fine. Now, in 1989, there was a big one. It was the Loma Prieta earthquake. My wife was picking up our then one-year-old. She was actually about 300 feet from where we're sitting right now, and the road started undulating like waves, like a sine wave, if you know what a sine wave is. And she said it made her sick to her stomach, not the motion, but just seeing a street do something that a street is not supposed to do, which is A, move, and B, make waves of asphalt. That was unforgettable. And then last week, I was sitting alone at home. I was reading email, and my house just had a little tiny jolt. I could hear the wood creaking. Everything moved. I checked to make sure I wasn't dreaming, and there was a slight sway to one of the chandeliers. Chandelier is a very fancy word for what I'm referring to as hanging in my kitchen. And then I actually got on the U.S. Geological Survey website to report it, because this is what I've started to do as a citizen. I find it extremely exciting, and I was very excited because I think I might have been the first person to report this 1.9 earthquake that I had experienced. Okay, so it's hard to remember safety when these things happen, but you want to worry about safety because it's such an amazing experience. As I said, I always go to a website to report it, and this is a really kind of fun way to engage in the society of science and earthquake detection and prevention. Well, Greg Beroza is a professor of geophysics at Stanford University who does this in a serious way for a living. He studies the details of earthquakes, their size, location, depth, and impact. He uses computational analysis of big data about earthquakes to understand the variety of ways that they manifest themselves, how we can measure them, and how we can prepare them for them. How we measure them and how we prepare for them. Greg, you use data about earthquakes to study them. What kind of data is useful, and how do you actually make these measurements?
Yeah, so let me first say that I'm impressed that you can feel a magnitude 1.9. You must be a very sensitive
It was very quiet, and I was very bored with my email.
Still, that's impressive. So let me say that we're currently not predicting earthquakes. So we have to be, our instruments that collect the data that I use to study earthquakes have to be running continuously all the time. So 24 hours a day, 365 days a year. We record the motion of the ground at each sensor 100 samples per second continuously. And we have networks of hundreds to thousands of sensors. So there's just a massive stream of data.
Are these sensors all around us and we're just not aware of it?
They're all around us, and I'm aware of it. But yeah, they're all around. So there's earthquake monitoring networks that span California. Absolutely.
Are they, for example, what is the probability that there's one near my house in a random spot?
What do you mean by near?
So that's my question is, are we talking there'll be one every couple of miles?
Yeah, we tend to talk in kilometers, but let's say your house is no more than 10 miles from a seismic instrument.
And were these installed by the government or by you?
These were not installed by me, definitely not by me, but they were installed by the government, primarily the U.S. Geological Survey. Some state agencies and some utilities have networks as well, but mostly the U.S. Geological Survey.
Forgive the interruption, but that's great. Okay, so please continue.
Yeah, fine. So anyway, we have these massive data streams. We used to just save the events. So the earthquakes that we identified as earthquakes, we would save that data, throw the rest of it away, actually. We don't do that anymore. We save all the data. So for the past 15 years or so, we have 100 sample per second data continuous over global seismic networks. So it's a huge amount of data to sift through, too much for us to really look at. And so we absolutely need the techniques of data science to extract as much information as we can out of it.
And so tell me the kinds of first order questions you would ask. So you have this data, you're finding out all over this grid of sensors who's moving and when. What are the kind of derived features that you pull out of this to say, okay, here's some higher level observations about what's going on seismically in this region?
Yeah. So there are a number of things we try to do. The most fundamental thing is to find the earthquakes, to create a catalog or a listing of earthquakes that includes their the time they occurred, their location, their magnitude, characteristics of how intense they are, that kind of thing. By using data science techniques, data mining, and so forth, we can increase the number of earthquakes in an earthquake catalog by a factor of 10 to a factor of over 100.
So this is by more precise detection of things that might not have been detected previously.
That's correct. And so we can't directly access sort of where the action is in earthquake science. It's at depth on faults, and so we have to try to effectively look into the Earth using seismology, using seismic waves, to find these small earthquakes, and that's what tells us what we know or think we know about earthquakes. So when we can see 100 times as many earthquakes, we get a much clearer view of what's going on.
So this, I find this fascinating because obviously the ones I talked about, with the possible exception of my 1.9, maybe Russ got lucky earthquake, those are the big ones. And now what you're describing is your ability through sensitive detection. Now, does that raise the issue of what constitutes an earthquake? Because if you have this long tail of smaller and smaller earthquakes, at some point is it difficult to tell the difference between an earthquake and kind of a normal non-earthquake event? Yeah,
so that's a great question. Actually, the tail is in the big earthquakes. So there are fortunately very few big earthquakes. There's lots and lots of small earthquakes. In fact, as far as we can tell, for each magnitude unit decrease, there's 10 times more earthquakes. So they follow what's called a power law. So they're huge numbers of small earthquakes, and they occur on the same faults by the same mechanism with the same physics as do large earthquakes. So if we can understand those small ones, which are happening all the time, the premise is we can understand better the big ones that we're all that are rare and that we're all worried about.
Yes, I'm struck by this argument. Really does seem to make perfect sense, which is if you want to use the methods of big data, and I'm using scare quotes there, if you want to use those methods, then you need a lot of examples. And if you're going to just sit around and wait for the 6, 7, 8 magnitude earthquakes, you're not going to have a lot of examples. So it really makes perfect sense to me that by diving into those lower magnitudes, you just get a richer sample. Is it all of the same cloth, though? Is it this? Do we believe that the principles we'll pull out about small earthquakes will transfer to big earthquakes? And what might some of those principles be?
So that's a great question, and it's something that seismologists spend a lot of time trying to find differences between small earthquakes and large earthquakes, because that would tell us something about the physics that's controlling their behavior. There have been lots of claims of finding those differences, but they tend not to hold up. And so as far as we can tell, and we can't see them as well, so it's a little, there's some uncertainty, but as far as we can tell, the little earthquakes are like the big earthquakes. There are, however, sort of different species of earthquakes. So there are things called slow earthquakes that happened that were discovered about 15 years ago. There are millions of them. We found millions of them now, and they were previously undetected. They happen on the deep roots of faults, and they're telling us something about the system, and we're still sort of puzzling out what that is.
This is the future of everything. I'm Russ Altman. I'm speaking with Greg Beroza about earthquakes, and you just mentioned slow earthquakes. What is slow about them? You said they're very deep. in the faults. Why are they called slow earthquakes?
They're called slow earthquakes. Well, they're actually, we call them low-frequency earthquakes because they lack the impulsive high frequencies that characterize ordinary earthquakes. That's a signature of either the slip or the speed at which they propagate across the fault being slower than usual. So that's why we call them slow. Exactly what's causing them to be slow, that's a matter of debate and active research. But there's no question that they are slow. We can tell that from their signature.
Can they be slow and big, or do they tend to be slow and small?
They can be slow and big. So the biggest documented slow earthquake is a magnitude 7.5 in Mexico. So that's a gigantic earthquake, much larger than Loma Prieta. That earthquake did not manifest in seismic waves. You could have been sitting right on top of that earthquake and you would have felt nothing.
Huh. And yet the plate tectonics and all the motion of these big earthly plates was still happening, was significant, got a big score on the Richter scale, so to speak.
Well, it's actually the Richter scale is based on waves, so it got a 0 on it. I mean, it didn't show up on the Richter scale, but the amount of slip and the area over which it occurred is equivalent to a magnitude 7.5 earthquake if it had happened suddenly.
Fascinating. So, so many things that I wanted to ask you about. So, first of all, one of the things that everybody worries about is there are the kind of common locations where we expect. So I live in California. I expect earthquakes. But every now and then we hear about earthquakes in unexpected places. I think I have a vague memory of some earthquake in the Midwest of the United States that was supposed to be humongous. Tell us about this. How good is our ability to characterize these earthquakes that are in normal places and that are in the less usual suspects? What do we learn from those, and how do they help us understand earthquakes?
Well, there's a lot in those questions because there were a couple of questions there. That's fine. So what you're referring to, I think, are the New Madrid earthquakes, which happened in the winter of 1811 and 1812 in the central U.S. Those are intra-plate or within-plate earthquakes. We have ideas, but we don't really know what they're doing there because most earthquakes happened on plate boundaries. And so they pose a particular threat because we don't know if they're going. We think the conservative thing to assume is that we'll have future earthquakes in those same places, even though we don't know why. So there has to be some uncertainty, more uncertainty than on a plate boundary attached to the recurrence of those earthquakes. And they're also in places that don't typically have earthquakes. So they're less well prepared than, say, we think at least, than say, California.
And their density of sensors might not be as high.
Their density of sensors is definitely lower. Definitely lower.
So, okay, so that raises the possibility that like nobody is 100% safe from an earthquake potentially happening, or is that not really a fair statement?
Well, it depends on what you mean. So most people travel. So even if you don't live in earthquake, a place of high seismic hazard, you're going to spend some time probably in places of high seismic hazard. There are vast tracts of the world where the seismic hazard is low, but it's not zero. And those places are particularly problematic because when an earthquake happens, it is, as you say, unexpected. And because it's unexpected, the places are in general underprepared.
Right. This is The Future of Everything. I'm Russ Altman. I'm speaking with Greg Beroza about earthquakes, places that don't expect earthquakes, and preparedness. And on that issue, I recently went to a talk by a guy who I would suspect you know, but I think his name is Goldfinger, actually. And he's done some work about big earthquakes in the Northwest, and has tried to be very vocal about the need to prepare for earthquakes that he's pretty positive will occur. And he gave a very interesting talk, which I can't go into the detail, and I wouldn't be able to do it justice, but it had to do with a historical record that he believes is showing repeated earthquakes that are quite huge in the Northwest of the United States. And he believes that the Northwest of the United States is totally unprepared for. What can science and engineering do to either help him get that message across, or to convince people that he's wrong, or whatever should happen?
Right. So what he's looking at are turbidite sequences. These are basically underwater landslides that the conjecture is that they give a record of past earthquakes. These things happen spontaneously as well. So if that were all that were happening, I don't think we'd be confident that there are earthquakes there. But what we can do is we know the relative plate motion. The Juan de Fuca plate is subducting underneath North America in the Pacific Northwest. We can see the change in shape of the Earth's crust, so-called strain, that's storing the potential energy that eventually has to be released in large earthquakes. And we know from drowned forests that drowned along the Pacific coast of the Northwest at that time.
These are forests that literally kind of
These are forests that were killed by saltwater intrusion. They didn't fall into the ocean, but their roots were suddenly tapping saltwater, and they died. And those forests are still there, some of them. We see tsunami deposits in marshes we see sand deposits caused by tsunamis in marshes. And there's even an orphan tsunami in Japan that happened in January 1700, killed people in Japan. And most of the Pacific Rim had a written history at that time. Pacific Northwest is an exception. And by looking at the rings in the roots of the trees that were killed by that saltwater intrusion, geologists have been able to find that in the winter of 1699, 1700 is when that big earthquake occurred. So we're absolutely convinced that the Pacific Northwest has had and will continue to have very, very large earthquakes that would likely be accompanied by large tsunamis.
So just so I can understand what you just said, are you saying that the records in Japan of a tsunami indicate that there must have been some earthquake, perhaps back in the northwest of America, that then propagated its way, and we don't have a record of the event happening in the northwest because there was no recording at that time, but we have the record at the other end of the Pacific that something happened. It was because you used this word orphan. I just want to make sure.
Orphan means that there was no agreed upon source for this tsunami. So it has to be generated by something. There are, however, Native American legends of a battle between thunderbird and whale during the evening, and sort of historical accounts, not written, but passed down that would have indicated that are consistent with a tsunami, a local tsunami at night in the winter, and the travel time for a tsunami to Japan matches perfectly. It's a great detective story.
It's a great detective story. So I want to get a little bit into this issue of earthquake prediction, and especially public expectations of what we should be able to expect about prediction. I'm sure it's a hard problem because a lot of people have been working on it. How should we think about earthquake prediction, and if it's the future of earthquake prediction, and how good it'll ever be?
Yeah. So I knew this was coming. So
Yes,
earthquake, we all would love to predict earthquakes. It's the holy grail of seismology. It's difficult, so we're not doing it right now, and it's intrinsically difficult. There's reasons to think it ought to be difficult, if not practically impossible. So I have a whole lecture on Stanford iTunes from 15 years ago or so about why earthquake prediction is so difficult. All of what I said in that, it's available for free, by the way. All of what I said in that is still true.
The last name is Beroza, Beroza.
Yeah.
Hit Google and take a look at that. Go ahead.
Yeah.
Shameless plugs are welcome here on The Future of Everything.
Well, thank you for that.
And that was not even shameless, by the way.
Yeah. So anyway, it would be negligent of seismologists, earthquake scientists, not to try to use the techniques of data science, machine learning, whatever, for earthquake prediction in the short term and earthquake forecasting in the longer term. I don't think we should not raise expectations that it's going to work. So I would advise skepticism, healthy skepticism, but it's due diligence to try.
This is The Future of Everything. I'm Russ Altman. More with Greg Beroza about perhaps a little bit more on earthquake prediction and definitely about human impacts on earthquakes next on SiriusXM Insight 121.
From the campus of Stanford University, this is The Future of Everything
I'm an informatics and data science guy.
with Russ Altman.
Welcome back to The Future of Everything. I'm Russ Altman, and I'm speaking with Greg Beroza about earthquakes, predictions, and new opportunities. So I get the feeling, Greg, from your previous comments that there are these sensors and that they're giving unprecedented amounts of quality and quantity of data, even with knowing the outcomes, like there was an earthquake, there was not an earthquake, and that can be used by these kind of very exciting new techniques in data science and artificial intelligence for learning. So should we now be going back over data that has perhaps already been gone over many times? And is it possible that we're going to learn new things, or have we perhaps already learned new things that wasn't obvious to our old-fashioned, if you will, ways of analyzing data?
Yeah, so that's a great question. We absolutely should go back to look at and to really exploit this old data. So there has been decades of work put in by network analysts, what we call seismic analysts, to pick wave arrival times for earthquakes in noisy data, and that provides tremendous benefit. We have millions, tens of millions of these labeled data examples, and that provides the necessary data for these deep learning methods that are bound to have a big impact.
Which are having huge impacts in image analysis, voice analysis, and now we're learning earthquake analysis.
Yeah, speaking of image analysis, we have a sort of an issue in that all of the data before about 1990 in seismology is analog. It's either recorded on film or on paper. So there are small warehouses full of seismograms that aren't being analyzed and contain who knows what. Right? So, I mean, we know they have earthquake records, but there's probably other things on there as well. And it's kind of an odd twist or odd combination, but machine learning is actually proving quite useful for analyzing these analog data, these old analog data.
So you literally like scan them in?
You scan them in, and rather than trying to get ground motion versus time, you work with the image itself using the techniques of machine learning. And we can do precision seismology, with this analog data through that approach.
And so you are kind of learning things from the old data, which might give us hope. Forgive me if I'm extrapolating too much, that these new techniques may yield clues that we don't expect or discoveries that are unexpected.
Yeah,
or am I overstating it?
Well, we hope there. I mean, yeah, we want to discover things, folks. So absolutely, you're not overstating it. What we're going to discover is hard to say. So what motivated us to work with this older data, so this is work being done with Bill Ellsworth in my department and Kai-Wen Wang, who's a graduate student, there was an earthquake control experiment where the USGS in an oil field in Colorado was given permission to sort of manipulate the fluid pressure in order to turn earthquakes on and to turn earthquakes off.
Whoa.
And so it was a famous experiment.
Who gives such permission, just out of curiosity?
Well, it was an oil company. I've forgotten which one, maybe
Okay.
Chevron. I'm not sure.
Okay.
But it was a great experiment. And we'd love to do that now, but we can't. Or, I mean, at least there are liability issues that would probably prevent that from happening now. So all the data from that experiment, all the seismic data is recorded on film. And so we've developed these processing techniques in order to extract information about this earthquake control experiment, something we couldn't do before, or we can't do now, but we have the data for the old experiment, and so we can use new techniques to get a better look at what actually happened during that experiment.
So you mentioned this idea of human manipulation of the surface and even the depths in order to kind of get earthquakes to happen or not happen. And so that leads me to, I think, a topic that we have to cover, which you've studied academically, which is fracking. And I guess a few years ago, there was a question about whether fracking had impacts on tectonics and seismic activity. You've made contributions there. What's the current understanding of the risks and realities of fracking with respect to earthquakes?
Yeah. So fracking can cause earthquakes. Hydraulic simulation is what we tend to call it. It can cause earthquakes, and we've documented cases where you can track the occurrence of these are very tiny earthquakes with hydraulic stages of hydraulic stimulation. Most of the earthquakes that were happening, and it's died down a lot now in the central U.S. and primarily Oklahoma, to some extent Kansas, were from a different mechanism. That is, it was injection of fluid, but it was from what's called dewatering operations rather than fracking. So fracking could definitely cause earthquakes, but in the case of Oklahoma, which had huge numbers of earthquakes, most of those were actually not caused by fracking.
Interesting. So there are other things that we're doing that also. I wanted to ask you that. Are there other human activities that have impacts on seismic activity?
Yeah, so there are a bunch of them, and we refer to them collectively as induced seismicity or human-induced seismicity. So injecting water into the subsurface is one way that we set off earthquakes. Impounding reservoirs, large reservoirs can trigger earthquakes. Extracting gas, that is pulling fluids out of the earth under the right circumstances or the wrong circumstances, can induce earthquakes. Mining can induce earthquakes. There's a whole range of human activities that impact the subsurface. And if you push a fault the wrong way or lubricate it or something, you can set off earthquakes.
Which I just find amazing because these are big, literally tectonic issues, and I think of humans as small and making little tiny dents, but it's just remarkable that some of these activities can reach a magnitude where it makes the Earth move.
Yeah, so I should say that most of these are small, and we can detect ground motion as small as a micron per second. So it's not necessarily a big earthquake. Sometimes it is, usually not, but sometimes.
This is The Future of Everything. I'm Russ Altman. I'm speaking with Greg Beroza about earthquakes, the physics of earthquakes, and our ability to understand them, detect them, measure them. So one of the things I was talking about earlier on during my intro is this obsession I have with getting on the U.S. Geological Survey website whenever I feel something that I think is an earthquake, and kind of thinking of myself as a citizen scientist, making a contribution by saying, here's where I am. It's very easy to do because they know where my computer is. They ask me this series of questions like, did anything in your house break? Would you call it a big, little, they ask about 4 or 5 questions. It makes me feel great. Is it a useful data source for you guys?
It absolutely is useful. So that webpage is called Did You Feel It?
Did you feel it?
Which is
yes,
sort of the standard question you get after an earthquake. And the USGS set that up and collects information from it. We can see fairly subtle wave propagation effects in people's responses if we have enough responses.
So tell me a little bit more what you mean by wave propagation.
So there's a layer. There are layers in the Earth's crust, and there are reflections off those layers which affect the amplitude of seismic waves at distance. And so seismic waves are what we feel in an earthquake. And so people perceive those differences. And if you're careful about sifting through these responses, because some of them are just bogus, right?
It's funny that, if I could just interrupt. It's funny that you say that because there's a comment field in where I do my reports at the end, and I always feel compelled to give them the history of my experience of earthquakes. So I say it's ridiculous, but I say like I was in the Loma Prieta. I've experienced more than 20 earthquakes. I feel confident that this really was an earthquake. It's like I'm giving my resume to make them believe me more, and it's just kind of ridiculous.
So that's cataloged somewhere. I know the people who run that, so I can ask them what they do with the comments if you want. But my guess is that probably not much at this point.
No, I would guess that too, and probably what it deserves.
But it is useful information because I said you're no more than 10 miles from a sensor, but they're large parts. 10 miles is a long way in seismology, and there are a lot more people than there are seismometers by 3 orders of magnitude probably in this country, and so for large parts of the U.S., we and to some extent rely on people's felt reports to get a more complete picture of earthquake activity.
And so that's really great news. So what you're saying is they can be integrated with your much more serious in the sense of controlled and engineered sensors. This is a useful adjunct data source.
Yeah, adjunct is a good way to put it. So there's a lot we can't do with it because it's not quantitative in the same sense, but it is useful information, and we need more Russ Altmans who can feel these small magnitude 1.9 earthquakes.
Now you have me totally doubting that experience. But let me ask you: is there, to finish up? We are all carrying around cell phones, and these cell phones all have accelerometers.
Yep.
Is there any opportunity to use that data to help you in your work?
Yeah. So people are doing that already. Again, it's lower quality data because it's moving around. It's maybe not fixed, but there are people who are using the sensors in cell phones as seismic instruments. There are other forms of data that we're collecting as well. So fiber optic cable, if you have a laser interrogator on it, can be used to sense a component of the motion of the ground. And there's an experiment going on at Stanford. My colleague Biondo Biondi is carrying it out to use cable on campus as
basically a big, huge sensor.
Yeah, well, actually a bunch of sensors.
Right.
So every 30 feet or so, there's a virtual earthquake recorder. So the data flood is only going to increase through these new sensor technologies.
And just to finish up, you said that website at the USGS was didyouFeelIt.com, .org? Do you know?
I don't.
Or did you feel it?
Did you feel it is the thing. And let me put in a plug.
Please do.
I've got airtime here for Earthquake Country Alliance. So for people who are looking to prepare for earthquakes. There's good information, concrete steps you can take to reduce your susceptibility to future earthquakes that are lying in wait in our future
And
somewhere.
say it one more time.
Earthquake Country Alliance.
There you go. Thank you for listening to The Future of Everything. I'm Russ Altman. If you missed any of this episode, listen anytime on demand with the SiriusXM app.